Okay, today we're going to learn something called dilations. Okay, so far we've learned many transformations, right? Which one have we learned? The first one was the yes, sir. Reflection. Second one was the yes. Rotation. Actually, second one wasn't rotation. Yeah, translation. Remember glide, and then we did glide and reflection. Remember, we put them together, and then the third one was rotation, right? Yeah, all right. So today we're gonna learn this transformation called dilation. What did you know? What did you notice about all the transformations that we've learned so far? There were the special, special transformation called isometry, right? But today, dilation, turns out this one is not an isometry. Okay, so let's somebody read this for us. How about let's see. How about yes, Samantha? Can you read this for us?
Reflections, translations, glide reflections, and rotations are isometries or congruence mappings. In this section, we consider a transformation related to the similarity rather than congruence. It is called a dilation. The dilation D
of OK
has center O and non-zero scale factor K. Dilation of OK maps any point P to a point P prime determined as follows.
Okay, good. So we're going to tell you what the definition of this dilation OK is. Okay, so dilation of O, comma K. The O is the point that we're dilating the points to, whatever this means. And K is a scale factor, as it says. So it's going to divide the definition of dilation in three parts. The last part is really easy. Do you guys remember from rotation? When you rotate a point around that point of rotation, it stays at the same place. So image and the pre-image is same. Same thing for dilation. If you're dilating a point that is on this point of dilation, the point stays the same. That's the third part. So first two parts is the interesting part. So first, it says when K is greater than 1, meaning when K is positive. Okay, so this scale factor, when this K is positive, P prime, which is my image of P, this is going to lie on, as you write this down, please underline, lie on where? It's going to lie on the ray OP. It's going to, so you're going to have to draw a ray. So that's sort of the key in understanding dilation. In order to find the image of points in dilation, you need a ray. And this ray, if K is greater than 0, meaning if K is positive, it's going to be on the ray OP. From your point of dilation to what you're dilating, right? You draw a ray, and it says on OP, but not exactly where, right? So let me show you where on OP the P prime will be. It's going to be on OP, and where is it going to be? It's going to be, no, it's going to be OP prime would equal to the length of OP prime is going to be K times the length of OP. So that's the definition of dilation, first part. If K is positive, okay, this is what's going to happen. Right now, you may not make 100%. You may not understand 100%, but as we do an example, it will make sense. But write this down right now, yeah. But I would underline, it's going to, the P prime, this is the key idea. The P prime will lie on this ray OP. And where would it be on this OP? It will be K times OP. That's where you're going to find OP prime. So write this down for now, and let's do some examples afterwards, okay? But write this down. Go ahead. So guess what second part is going to tell you? It's going to say when K is what now? Less than 0, meaning when it's negative. When K is negative, so it turns out P prime would not be on this ray, but it will be on the opposite ray. That's the key. Please underline opposite of, it's going to be ray opposite ray of this OP. So it will not be on OP this time if K is negative. But the OP prime will be in the similar place. It will be on the absolute value of K times OP. Okay. So why do we need the absolute value of K? Because K is now negative, so we need the absolute value. The distance can't be negative, right? So it's not going to be on the OP. It is going to be on the opposite ray, okay, or ray opposite of OP. And like I said, it may not make sense 100%. Don't worry about it. We'll do an example. It'll make sense afterwards. Okay, so write this down though. But please note that if K is negative, would it be on this OP? No, it'll be on the opposite ray, okay, or ray opposite. And of course, the last part is simple. Like I said, if the point is on the point of dilation O, then it's going to stay at the same place, okay? That's what it means. So write that down. I'll wait for you. Number 3. Yeah, number 3 is obvious. Just like rotation, right? If the point is on the point of rotation, it doesn't move. Same thing for dilation. If the point is on the point of dilation, it's going to stay at the same place, even if you dilate, okay? And also, if k is absolute value of k, I should say, if absolute value of k is greater than 1, the dilation is called expansion. Because k, right, the k is that scale factor, right? So it's going to, what do you think is called expansion? It's going to, the pre-image, yeah, the image will be greater than the pre-image, right? It's going to get bigger. What do you think would happen if absolute value of k is less than 1, meaning like 0.2 or 0.5 or negative 0.3 as a matter of fact? It's going to shrink, yeah, and it's called the contraction. So if absolute value of k is less than 1, the dilation is called a contraction. Okay? And this dilation, let's do some examples. That will make more sense. Okay, so write this down for now, and then let's do some examples, okay? So let's do an example. Hopefully this will make it a lot more clear. You may not understand the definition 100%, but let's see whether we can follow the definition to do some examples here. So it says find the image of triangle ABC under expansion of D sub O comma 2. So we're going to dilate the points around O with a scale factor of 2. So here is the picture. We got a triangle ABC, okay? Now, look at the definition that you just wrote down. Look at k, value of k, because value of k is what makes it, right? Whether we should go to the first definition or the second, right? Which one do we use? The first one or the second one? First, because k is now positive. K is positive, so we use the first definition. What does it say? So let's look at A. Where would A prime be then? Since k is positive, A prime must be on the ray of OA. Not AO, that's different. OA. From your point of dilation to that point. Yes? Because it said OP, right? Now my P is A, okay? So it's going to be on this ray OA, right? Now, where on this OA will the A prime be at? For example, like whatever, so look at my case. K is 2, correct? Yeah. So OA prime better be twice as much as OA. So you see how the A prime will be right around here somewhere? You see what I mean? That's what it's saying. What about C? Let's look at C. I'm going to draw a ray from O to C, and of course I'm going to extend it. And where will C prime be? Twice as much as OC, whatever the OC is. And so will the B prime be right there. It got cut off. But you see how you get a triangle again, right? And you see how the two triangles, look at the two triangles. What do you think these two triangles are? Turns out, yeah, they turned out they're similar. And as you can see, the triangle, my image is bigger than my pre-image, right? Yeah, original, the pre-image. Because it's an expansion. My K is, absolute value of K is greater than 1. Do you see how the dilation works? So that's what that definition is saying, right? That's all it is, okay? So go ahead and take a look at it. And also, look at this. This is what we get, right? Look, if I'm dilating O up to of triangle ABC to A prime, B prime, C prime, my OA prime must be twice of OA. OB prime must be twice of OB, right? And OC prime right here, this is twice of OC. That's right. This is from the definition, right? So let's look at example 2. It says now find the image of this pre-image triangle RST under the contraction. What do you say this is contraction now? Yeah, look at the value of K. It's the absolute value of K is less than 1, isn't it? So it's going to get smaller. It's going to shrink. So now before I even give you all the points of RST, you should be able to tell me. This is what we're doing right now, right? Yeah. Dilation of O around O with the scale factor of 2/3. Triangle RST will map to triangle R prime, S prime, T prime. What would the length of OR prime be? Without even me giving the points, you should be able to know what the length of OR will be. How about Yechan?
2/3 times OR.
Exactly. That's by the definition, right? Can you then tell me the rest? What about the length of OS prime? What would that be? Esther. Yeah, 2/3 of OS. Good. What about then OT prime? How about Jason? Yeah, 2/3 times OT. This is just straight from the definition, right? Does that make sense? So notice, as you can see, my triangle is going to get smaller. So here's the triangle. which one is my pre-image? Black one or the red one? The black one. The red one is my image because it's going to get smaller. Watch how it gets smaller. Watch. Let's look at OR first. I mean OR prime. OR prime, notice my K is positive. So it's going to be on this ray OR, right? You see the ray OR? It's going to be on this ray. And how do I get R prime? Because if I were to divide this OR into 3 pieces, R prime would be on the 2/3 of it. Does that make sense? Yeah. So look at OT. The T prime OT, the T prime will be on the ray OT. And if I were to divide this segment OT into thirds, the T prime will be on the 2/3 of it. Same will work for the S. Does that make sense? Do you see how this dilation works? Okay, so we have seen so far the dilation where K is both positive, and one of the example one, the K was the absolute value of K was greater than 1. Here, the absolute value of K is less than 1. That's how we get a contraction to that. And then the other one, when absolute value of K was greater than 1, you get an expansion. So very good. So take a look at that. Okay. So take a look at these triangles. Let's look at the example 1 and 2 together. Okay, as we said before, look at these 2 triangles. The 2 triangles look what? They look like they are similar. Turns out they are going to be similar. And actually, that's going to be our theorem. It's going to say dilation, right? If you dilate a triangle, it's going to be a similar triangle. So any polygon as well, because polygons are made up of a bunch of triangles. So once you prove that, then you can use that for polygons. Now, what about? Let me ask you this. What is then the scale factor of, let's see, AB? Look at the AB, okay? Segment AB to A prime B. Let's look at AC, got cut off. AC to A prime C prime. What do you think the scale factor of these 2 segments might be? Anybody any guess? It'll be 1 to 2 because my K is 2, right? You see what I mean? So if that's true, and I'm going to just tell you that the 2 triangles are similar, okay? What do you know about the scale factor? I mean, what do you know about the ratio of the areas of these 2 triangles? What do you think it would be? It would be 1 to 4. Wouldn't it be? Because remember we learned this. Yeah, you square the scale factors. You guys remember that? The ratios of their scale factor. Now, what about then for the second example? What will be the, so we got to go from pre-image to image. This case, yeah, it'll be 3 to 2, the scale factor of the corresponding size, right? So then what about their areas? The ratios of the area will be 94. Does that make sense? So that's what this is saying right here. Okay, so you see the 2 triangles are similar, and if they are, compare the ratios of their area. It's going to be squares of their scale factor. Does that make sense? Now, which one have we not done? When K is negative. Let's look at when K is negative. Here we go. So here we go. We're going to now finally look at the case where K is negative. In this case, K is not only negative, it's actually the absolute value of K is less than 1. So it kind of puts them together. So we want to know, find the image of figure. Now this time it's a figure, F. And now this figure happens to be a turtle. So, yeah. Okay, so there's a figure turtle. And the O happens to be right here. By the way, where O is, I give it to you. I tell you where the O is, okay? So some of you are asking, well, how do you find O? I give it to you. Okay. Anyway, so it says find the image of the figure F under the contraction. Do you see why it's a contraction now? Yeah. Because K, the absolute value of K is less than, no, it's not because it's negative, because but it's absolute value of K is less than 1. Now, let me ask you this. Look at the definition. In this case, which case is this? This is the first one, second, or the third? Second, where K is negative. Where would P prime be? That's a hint in terms of figuring out what this... Would it be on this ray OP? No. No, it's going to be ray opposite going this way. Does that make sense? And you're going to start at O. Does that make sense? So the OP will go this way. Now, where would P prime then? Yeah, if this is like unit 1, then it'll be half as much, right? So it'll be around here somewhere. That's where P is, right? Does that make sense? Now, then I want you to figure out what this total will look like if you did this dilation.
It would be small.
Would it be upside down? Would it look like the same thing as this? How would it be? Go ahead, everybody think about it. Oh wait, okay, everybody think. You work as a group, Ask your team, okay? So, to actually figure out how this total will look like, let me give you a hint. Let's think about, you see the back of the total on the very top? Let's put a point there, let's call it Q, okay? If I were to put a point Q there, where would Q prime be? It'll be on the opposite ray of OQ, correct? So it'll be right here. You see how OQ will be here, and then it'll be opposite way this way. So the top of the back, right, the back part, the top part will be down here. So the shell. So do you think? What do you think? Do you see how this will be upside down?
Yeah.
Yeah. So look at the head. The head is right here, right? So it's going to be on the other side. So it's going. My head got cut off. Sorry. But you see. Okay. You see how it'll be upside down. Does that make sense? Okay. Hold on. Shh. Okay. Do you see? Why is it upside down? Okay. Listen. Because we're not doing a reflection, are we? We are dilating. So Amy, look. If there was a point on top of this the shell, right? It'll be right here. You see, let's say put a point Q there, right? So draw a ray OQ. The Q will be on the opposite ray of OQ. It's not going to be on top this way, would it? So you gotta follow the definition of dilation, right? So by following the definition of dilation, if there's a point Q, the Q prime must be on the opposite ray of this OQ. Wouldn't it be over here? So that's where the P is going. Q prime will be. So it's got to be underneath the P prime. So that's why it's going to be upside down this way. Does that make sense, guys? Yeah. Okay, so please note that this is what it will look like when you have a negative dilation in this case. Okay, so it'll get upside down. Now, another thing that's interesting is instead of this the K being negative half, what if it was negative 1? If it was negative 1, it's going to be same as something. I want you to think as a team, what do you think this transformation will be if it was negative 1? If it was negative 1, think about it. Everybody think about it. What do you think? So, what did your team come up with? If the K happens to be negative 1, not half in this case, it is actually same as what? Josh.
It's the same, but it's upside down.
Well, it is upside down right now.
No, it's the same as previous.
It's the same size.
Okay, the size will be same, yes. In other words, but that's same as what? Which mapping that we talked about? It's same as half turn. It'll be a half turn, wouldn't it? How many of you came up with half turn here? Okay. You see why it'll be a half turn? Because like Josh said, listen, it'll be same like this, but then, right? It'll be like exactly the same distance away from, right? P will be the same distance with OP, right? On the other ray. And you're gonna have the same turtle upside down. Isn't that a half turn? Okay. All right. So let's summarize this right now. Here we go. Okay. So somebody read this for us. How about John? Can you read this for us?
If the scale factor in example 3 was -1 instead of -1/2, the figure f prime would be congruent to the figure f, and the transformation would be an isometry, equivalent to a half turn. In general, however, as these examples illustrate, dilations do not preserve distance. Therefore, a dilation is not an isometry unless k equals 1 or k equals -1.
Yeah, so there are some cases, but it's not generally, right, an isometry. Does that make sense? All right, let's move on to this. How about somebody read this for us? Go ahead, Brianna.
A dilation always maps any geometric figure to a similar figure. In the examples above, triangle ABC is similar to triangle A prime, B prime, C prime. Triangle RST is similar to triangle R prime, S prime, T prime, and the figures F is similar to the figure F prime. For this reason, a dilation is an example of similarity mapping.
Yes, and actually this is going to be our theorem. We're going to say the dilation is what? Not an isometry, but yeah. So actually we're going to talk about it in terms of a triangle. So here it is. If you were to dilate a triangle, guess what you get? You get a similar triangle. So write this down. A dilation maps any triangle to a similar triangle, turns out. Okay, so write that down. I'll wait. Okay, and we're going to actually prove this. Okay, so think about how you go about proving this. Okay? So to prove this, guys, we want to show that triangle ABC is similar to triangle A prime, B prime, C prime. To prove it, by the way, there are two ways to do this. You could use the algebraic proof, right? Coordinate geometry proof, or just two-column proof, right? Prove it directly that way. We're gonna let's just prove it directly. Okay, we could actually use coordinate geometry proof, but how would you do this? Proving two-column proof. What would you need to say? What would you need? We need triangle. First of all, we need two triangles similar, right? Yeah. How many ways do we know how to show that the two triangles are similar? There are 3. First one was what? Angle similarity. theorem, a postulate. What was the second method we learned? Side, angle, side, similarity theorem. And then third? Side, 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 similarity theorem, right? Was there angle, side, angle? That's AA. Okay, that's AA. Okay, so we need one of those three. Now, to show that the two triangles, ABC and A prime, B prime, C prime are similar, what do you think we're going to need to show? The corresponding sides are in proportion, then you'll be done, right? So if I could show that the three corresponding sides are in proportion, I'll be done. So is there a way to show, let's just look at AB and A prime, B prime. Is there a way to show that these two sides are in proportion? Oh, couple of people see it? Yeah, if I could show, is there a way to show that AB is similar, in proportion to A prime, B prime? Okay, Nicole.
Isn't it like the median of that triangle?
Well, K could be any number. It doesn't have to be 2. So but that's a good idea. Actually, which triangles were you looking at?
That one, the blue one.
Name it.
I don't see the letter. Like K.
Oh, here.
Oh, yeah. O, K, no, like, oh, A prime, sorry.
Okay, O, A prime, B prime, and what else?
A, O, B.
Yes. It turns out, if you look at these two triangles, O, A, B, and O, A prime, B prime, something interesting. You should know something interesting. From the definition of dilation, anybody see anything interesting? What can you... Oh, okay. Nicholas.
K times AB equals A prime B prime.
That's not what the definition of dilation says.
Oh.
Not the AB to A prime, B prime.
Okay.
It's something else. Tony?
Well, we could prove the triangle OAB is similar to the triangle OA prime B prime by
Yeah.
by SAS.
By SAS is correct. Grace, did you want to add something to that? How would this be SAS? Oh, okay. Why would this... Tony is correct. By using side angle side similarity theorem, we could show that the triangle AOB and A prime B prime, A prime O B prime are similar. Samantha, how would you do that?
Because the definition of a dilation says
Good.
that, OP prime equals K times OP, which means that they're in proportion. And so then you can say that for the sides, and then they share angle O.
Exactly. So what can you tell me about, guys, OA prime versus OA, Grace? What do you know about OA prime? Is how many times as OA? K times. What about OB prime? Is same as how many times of OB? K times, right? So look at these two sides are in proportion, but where's the angle? Don't we need the angle in the middle? Well, they share the same angle in the middle. So by the definition, from the definition, we know that OA prime is absolute by of K times OA. OB prime is absolute by of K times B, right?
Yeah.
Yeah, and don't they share the same angle?
Yeah.
Well, from there, we could say then the two triangles are similar. Well, what do you know about similar triangles? Especially the corresponding sides. In terms here, AB and A prime, B prime, they're in proportion. And I can even tell you what the proportion is going to be. It's the absolute value of K, isn't that right?
Yeah.
So, could we do the same thing for all three sides?
Yes.
Okay, you could do the same thing for all three sides. And all three sides are going to be in proportion. So what do you know about the two triangles? Triangle ABC will be similar to triangle A prime, B prime, C prime because
Because of
side, similarity theorem. Does that make sense? Okay. Do you see how the two triangles are similar? So that was kind of interesting, right? You got to look at that other triangle that gets formed. So
Wait, but so
hold on. So does that make sense? And from here, we get three corollaries. Okay, so let's look at those three corollaries right now. Okay. So the first corollary, what do you know about similar triangles in terms of their corresponding angles?
Congruent.
They're congruent, right? So guess what? It's going to say corollary, a dilation maps an angle to a congruent angle. Okay, that's pretty obvious. Okay, so write that down. A dilation maps an angle to a congruent angle, basically because of the theorem, right? Because you get similar triangles. You know that the corresponding angles of similar triangles are congruent. Okay. So I want you to take a look at this picture again. The second corollary has to do with this. Okay, I want you to look at segment AB and A prime B prime. Okay, and you have just take a look at this OB prime. Okay, what can you tell me about this angle right here? A prime B prime O and ABO. They are same, right? Because remember these two triangles were similar, right? The small one and then the big one, right? So if two lines are cut by a transversal and what are these? Corresponding angles are congruent. What do you know? These are parallel, right? Do you guys remember this? So guess what this corollary is going to say?
The side of the triangle.
Yeah, so the dilation of OK maps every segment to a parallel segment. And not only that, the segment is absolute value of k times as long. And we know why it's absolute value of k times long, right? Because we know that they're similar with the scale factor of k. Does that make sense? So dilation of OK maps every segment to a parallel segment, absolute value of k times as long. Okay, so write that down. And of course, it comes from that previous theorem. Okay. And let's go back to that triangle again. What do you know about then the areas? The image versus pre-image. If you were to look at their ratio, it's going to be k squared times, not just k, right? Remember, areas? So write this down. The dilation, here we go. The dilation of the k maps every polygon to a similar polygon whose area is it k or k squared? K squared times as large, because we're talking about area now, not just the length, right? So dilation, okay, maps every polygon to a similar polygon whose area is k squared times as large. Okay, write it down. So take a look at this now. This is showing you, if we had to prove this using coordinate geometry proof, that you could say, okay, if you have a, xy pair, if you were to dilate this, it will be at kx comma ky, where k is the scale factor. And of course, where must O be in order for this to work?
In the middle.
At the origin. If it's not at the origin, would this work? No. Okay. And of course, if k is negative, as you can see, it will be on the other side, right? On the opposite ray of OP, right? So it'll work as well if k is negative. Does that make sense? So this is really nice to know, because sometimes on your homework tonight, they're going to ask you to figure out how an order pair gets mapped if you're dilating on a point O, where it's the origin, with some k. And without actually graphing, knowing this mapping, right, it may be easier for you to do. So I would write this down, okay? So because you're going to need that if the O is at the origin. Okay, please remember, O must be at the origin. Will the O always be at the origin? No. Okay, not necessarily. Okay. So let's do example 1. Now I want you to all try this example 1. This is case where the dilation is not on O. Okay, it's on A. So it doesn't have to be always on O. Okay, on origin. So I'm sorry. Okay, so you got A right here at 2, 3, right? That is the point of the dilation. Okay, and if my B is at 6. Oh, it says 7, 5, but it should be 6, 5, right? So if
6, 5.
okay, so 6, 5. Okay. No, but I wrote down 7, 5. Okay, it says 6, 5. Where would B prime be if you were to apply this dilation of A comma negative 2? Now this time I did this because the dilation is not on O anymore. Okay. Go ahead, everybody try. Where would this dilation would take this B to? Find my image. Go ahead, everybody try. I'll wait. Okay. So first of all, my k is negative. So where would B prime lie on? On the opposite ray of what? AB. So your starting point is where? A. So it's going to be on the opposite. This is AB right here. I have to go this way, right? It's got to be on this ray. Would it be? Would it not? This is, no, because k is negative right now. K is negative 2. Okay, so if k is negative, the P prime and B prime will be on the opposite ray. Now, where would on this ray be? Yeah, double of this distance. So I could kind of go, okay, how much is, so I have to go down 1. Okay, so as you can see, I have to go down 1 to the left 2, down 1 to the left 2, right? So do the same thing, how much? Twice. Go down 1. So where would it end up? What? I have to go down, actually, how much? 2 and to the left 4. So I have to go down 2, left 4, do it again. Down 2 to the left 4. There's your B prime. So B prime ends up at where, guys? Negative 6, negative 1. Do you see? Because you got to go twice as much distance. So this to go from here to here. Does that make sense? So as you can see, the distance from here to here, right? How do I know this distance? This distance, I have to go down 2, and to the left how much? 4. So I have to go down how much then? Do the same thing. Down 2, to the left 4. Do it twice, right? Does that make sense? Now, can you do this? If it's half, where would it be? If it's negative half, it will be where? Which is right here, right? Do you see my B double prime then? Does this make sense? Have a good day, guys.